So I want to start by recapitulating a few things from the last 2 days, and some of them very helpfully are still on the board, so that saved me a little bit of effort. So I remind you that gamma, the symbol gamma, denotes a symmetrized bidisc, so it's that set up there, a set in C2, compact, with the various properties that I described. And a gamma contraction, so if S and P are commuting operators, on a Hilbert space H, then SP is a gamma contraction so this is a definition. It's defined to be a gamma contraction if for all polynomials P, I think I used G, polynomials G in 2 variables, the norm of GSP is bounded by the supremum of the modulus of G on gamma. So that can also be expressed by saying that gamma is a spectral set for the pair S comma P. And the connection with commuting pairs of contractions is simply that if A and B, if norm A is less than or equal to 1, norm B is less than or equal to 1, and AB equals BA, then you can form the symmetrization A plus B AB of these commuting operators, and that is a gamma contraction. And the goal in this lecture, as Vasily said, is to develop a functional model for gamma contractions. We have a very useful characterization of gamma contractions. If you have a commuting pair of operators, S comma P, then it turns out that S comma P is a gamma contraction if and only if for every alpha in the disk, this operator here, 2 minus alpha S star 2 minus alpha S minus 2 alpha P minus S star 2 alpha P minus S is a positive operator. So I think those are the main things that we need to remember from the previous. Yeah, oh, there's also one other useful thing. We worked out a model gamma isometry last time. So if you take an operator A on a Hilbert space E, and you form this pair of Toeplitz operators on H2 with values in E, then this is a model, this is a gamma isometry, and moreover, it's a pure gamma isometry, and moreover, every pure gamma isometry is of this type, with the numerical radius of A being less than or equal to 1. So that's more or less where Agler and I left it in 2003. And we did pose the problem at the end of our paper on this topic. Is it possible to develop an Hodge-Feuillage type model for gamma contractions? We couldn't see how to do it at that time. But then it was picked up relatively recently by mathematicians in India, mainly in Bangalore. And they have really finished off the project very nicely, I think. And I want to describe how they did that. So, first, they noticed something about this characterization here. So let me rub this out. So this characterization that we used is useful, but they found a rather nicer way of phrasing it. So this is a small theorem of Bhattacharya. And so we assume that we've got a commuting pair of operators on a Hilbert space H. Then S comma P is a gamma contraction if and only if there exists an operator capital F on is it dp or dp star? Yeah, dp, the defect space of P, such that the numerical radius of F is less than or equal to 1, and S minus S star P is dp F dp. Eigler and I sort of knew this, at least in the case when norm P is less than 1, so let's just go back to this characterization here, and let's call that rho of S comma P. So so let rho of S comma P be this thing, 2 minus S star 2 minus S. So I'm putting alpha equal to 1 here, minus 2p minus S star 2p minus S. And let's just expand that thing. So I take these two and then these two, that's 4 times 1 minus p star p. Note that the S star S terms cancel here. So what we're left with is 2 into S minus S star P minus 2 into S star minus P star S. And so if you've got a gamma contraction, so if SP is a gamma contraction, and let's suppose that for the moment that norm P is strictly less than 1, then according to this characterization up here, and for all omega in the unit circle, if you look at a quarter rho of omega S comma omega squared P, that's got to be positive. So 0 is less than or equal to that, which is 1 minus p star p minus a half omega into s minus s star p minus a half omega bar s star minus p star s. And so you can write this as so this is the real part of omega times s minus s star p. And so that says so we have that for all omega in the circle. So in the special case that P is a strict contraction, we can write this criterion, or at least in the case for alpha of modulus 1, in this way. And now because I've assumed that P is a strict contraction, this is boundedly invertible, and so I can multiply by the inverse of d sub p on either side. And so I get the real part of omega. So this is d sub p squared here, of course. So I multiply on the left by d sub p inverse. And that's less than or equal to 1. And so if I call this operator here f, that says that the real part of omega f is less than or equal to 1 for all omega, and that's the same as saying that the numerical radius of f is less than or equal to 1. So that proves necessity in this theorem of Bhattacharya. That proves the necessity in the case when P is a strict contraction. In the case when P isn't a strict contraction, we didn't notice this as a fairly simple calculation to show that nevertheless there is such an f, and it has to be numerical radius less than or equal to 1. And also that's sufficient for S comma P to be a gamma contraction. And that's in some ways rather nicer characterization, because instead of having to look at a whole one parameter family, as in this characterization, here we have a single operator. And this operator then goes on to play quite a role in the in the functional model as well. So I think that was a very useful observation to make. And this f is called the fundamental operator. Of the gamma contraction S comma P. Let me recall a couple more things from previous lectures. Firstly, remember the formula for the characteristic operator function. So P is a contraction. We're thinking about gamma contractions S comma P. That means P is a contraction, and so it has a characteristic operator function which is minus p plus lambda dp star 1 minus p star lambda inverse dp, restricted to the defect space dp, and that's an operator for each lambda. That's an operator from dp to dp star. And that plays a role in the non-Fourier model. And so the model space in the pure case, so when the powers of p, the adjoints of the powers of p tend strongly to 0, HP is defined to be H2 with values in dp star, orthogonal complement theta sub p, H2 with values in dp. And using some of the same ingredients as well as this fundamental operator that I've just introduced, we can write down the functional model. So for pure gamma contractions. So gamma contractions I just defined. A pure gamma contraction is a gamma contraction S comma P in which P is a pure contraction. So powers of P star tend strongly to 0. And this is due to Bhattacharya and П.Л. in 2014. So let SP be a pure gamma contraction. On H. And let, say, G be the fundamental operator of S star comma P star. So if SP is a gamma contraction, then clearly the adjoints S star P star are also constitute a gamma contraction. Then
sorry, but if P is pure, P star is not obligatory pure.
No, that's true, but it doesn't matter. Then the model is the following. SP is unitarily equivalent to S wiggle P wiggle on the model, the same model space as before, on this space HP up here, where P wiggle is what we've met before. It's just the Nagy-Fourier model of P. So it's just the compression of the forward shift to HP. And the more exciting part, what is S wiggle? So the model for S well, it's the compression to HP of a model gamma isometry. And furthermore, what I called A in my description of the model gamma isometry before is now G star. So it's G star plus G times Z. Oh, yeah, that's it. So this Toeplitz operator acts on H2 of dP star. So that's, once you know the Nodge-Foyash model for contractions, then this is really a very simple kind of extension of it to gamma contractions. Until I want to prove this. So let me recall a few things. So we introduced an isometry, W, going from H into H2 dt star, dP star, because now the contraction is called P, and a vector x in H maps to the sequence dP star x dP star P star x dP star P star squared x, and so on. So we'll be using this, of course, and the range of W we showed last time on Tuesday is precisely the model space HP. And now let's just remind ourselves what the operator G is. G is the fundamental operator of S star P star, and fundamental operators are defined here, only it's S star P star rather than SP, and so in this definition of the fundamental operator we have to put a few extra stars in, and we get S star minus SP star is equal to dP star G dP star. So that's the definition of G, the fundamental operator. And of course G, we have to say G is going from dP star to dP star on defect spaces. And now I claim that, let's see, let me draw a diagram. So we've got H2 dP star, H2 dP star, and we've got W star. W is an isometry, so W star is partial isometry from the range of W into H, and we've got our operator S here, and we've now got our operator T of G star plus ZG. Down here. And I claim that that commutes. So in other words, W star TG plus Z TG star plus ZG is equal to S W star. So that's what I want to prove. So the first step is to work out what the adjoint of W is. So W goes from H into H. So W goes from H into H2 of dP star. So let's work out what W. So W star goes from H2 dP star. So an element of H2 dP star could be something like that. Z to the n tensor y, and it goes into H. So for x in H, y in d P star, and n greater than or equal to 0, we could apply W star to this vector in H2 dP star. And what do we get? Well, we get Z to the n tensor y in a product Wx. And Wx, just barely visible on the right-hand board there, is dP star x dP star P star x, and so on, and corresponding to Z to the n, we would have d P star to the n x in H2 dP star. And so all that happens is that you pick out this term corresponding to Z to the n, and that would be in dP star, but that's the same as in script h, of course, just a subspace. And so we could pull these over to the other side, and we get p to the n dP star y x in a product x in h. So what this shows is that W star applied to Z to the n tensor y is p to the n dP star y. And now I'm trying to prove that W star T G star plus ZG is SW star. So let's work out W star T G star plus ZG on Z to the n tensor y. Well, that's W star. Now this is just analytic Toeplitz operator. You're just multiplying G star plus ZG times this function in H2. And so what do you get? You get Z to the n tensor G star y from this one, and then from ZG you're going to get Z to the n plus 1 tensor GY. And so from this, the formula in the previous line, that is p to the n dp star g star y from this term plus p to the n plus 1 dp star gy. Yeah, that's right, isn't it? gy. And we want to compare that with SW star applied to the same element. So that's S, and W star applied to Z to the ny again is just P to the n. dP star y from this equation up here. Now S and P commute, so I can pull this P to the n out in front. And so we have two expressions for the two sides of the equation I'm trying to prove. So it ought to be the case that this is equal to this, if what we're trying to prove is true. So let's look at the difference. Let's look at W star T G star plus Z G minus S W star applied to Z to the n tensor y. So that's this expression minus this one. And so P to the n factors out, and we get dP star G star y plus P dP star gy. Let me put the y's at the right hand side. P dP star y minus S d P star y.
P star subindex.
Thank you, yes. And let's call that P to the n hy. So I'm going to call all this thing h. And h is supposed to be 0. So let's see why h is 0. Well, we could look at h times dp. Because h goes from the defect space dp into the Hilbert space h. So if we look at h times dp, it's dp star g star dp star plus p dp star g d.
From dP star, this h works from dP star, not from dP.
Yes, thank you. Is that right? Yeah, these should all be stars. You're right, yes. Minus S dP star squared. Now this where's my definition of, here, yeah, now I want to use this. So this term here is P times S star minus SP star by the definition of the fundamental operator. Now the adjoint of this is this term here. So this is the adjoint of S star minus SP star, so it's S minus P S star. And the third term is S dP star squared is 1 minus PP star. And now if you stare at that for 10 seconds, it all goes up in smoke. Let's see if we can see why. Well, I could cancel this S here with this identity here. And then this term here, minus PS star plus PS star there, they also cancel. And what we're left with is minus PSP star plus SPP star. But PS is equal to SP, so they cancel as well. So this term cancels with that term, and so we do indeed get 0. I thought that was a very pretty little calculation that they found. So when do we start? 5 past. So I reckon I have 5 minutes, do I? Right.
Choose the perfect time for the break. It doesn't matter exactly.
No, fair enough. Well, right.
Sorry, can I ask a question?
Sure.
The idea behind the calculation was to choose an operator like the model operator from your theorem.
Yeah.
So try to choose the topless operator, this compression of topless operators model space, and then making calculations. Because for me it's unrealistic to guess such a choice without any
Yes.
without any idea. Or there is something other behind the calculations.
Well, of course, I don't know how they came up with this. They knew they had to find an operator of numerical radius less than or equal to 1, and then they looked at what such operators were hanging around, and they found this fundamental operator, and they tried to see if that worked. I guess, but as I say, I don't know. I wasn't there. So, but anyway, it certainly does work. And so then I think we should, that more or less does it if you just look at it in the right way. I guess I should just go back to that that commutative diagram that I drew. Is that still? Oh, I seem to have rubbed it off.
It's there.
Yeah. So we had this diagram, H, S, H2, dP star, H2, dP star, and this is W star, and this is T, G plus, G star plus ZG. So really that more or less does it. What are we trying to do? We're trying to prove that S is unitarily equivalent to the compression of this Toeplitz operator to the model space, H sub P. Now this W star is a, as I said, co-isometry. So we have so SW star is equal to W star times this Toeplitz operator. Now if you just take adjoints, so you get W S star equals the Toeplitz operator times W. So that tells you that the so that says the range of W is invariant for this Toeplitz operator. And the range of W, which is H sub P, is invariant for this Toeplitz operator. And so it follows, if you take U to be the range restriction of W, so in other words, U is just W regarded as going from H into the model space HP, then you do indeed get that.
I'm sorry, but this Toeplitz operator is not self-adjoint, so it's changed index.
Ah, thank you. Yes.
The bar and contraction, no?
Yeah, you're right. Wait a minute. Let's see. Yeah, once again, I've got my stars mixed up, unfortunately. So maybe this is a good time for a break. Finish off. The main part of the proof was that commutation. So this relationship so we had SW star equals, I'll copy it from my slides this time so I get it right. Equals W star times this right, G star plus G Z. So that's where I got to in the proof, and then it's almost finished, but I went slightly wrong in the conclusion. So let's take adjoints. WS star is the adjoint of this Toeplitz operator times W. And so that says that the range of W is invariant for this adjoint of a Toeplitz operator. And then we have this, now we have this diagram again. So we've got our operator S, we've got H2 dP star, H2 dP star, and if we write W here, and here would be, I'm probably going to get the stars wrong again. No, maybe it's safer to stick with W star here.
Now it's star. Okay.
And now this should be T, G star plus GZ. And that all commutes. So if you define U from H into HP, this model space, then you get that U S star U star is the and we already have from previous construction of the Nodge-Foyash model that UP star U star is just TZ star restricted to HP. And so taking adjoints in both of these, you get that S comma P is the compression to HP of this pair of operators. So. And so that is the theorem of Bhattacharya and П.Л. Now that was only, of course, for the case of pure gamma contractions, which is where Bhattacharya and П.Л. left it. And then the question is, can you do the same thing for a general gamma contraction? And naturally that's somewhat more complicated, but it was done by a former student of Bhattacharya, Jaydev Sarkar, in 2015. Reference on the screen there. And so now let SP be a completely non-unitary gamma contraction. So that means it's a gamma contraction, and it means that P as a contraction is completely non-unitary. Then SP is unitarily equivalent to S wiggle B wiggle on the the Nodge-Foyash model space. So we saw this on a previous slide. So you take H2 of dP star, direct sum delta sub P L2 of dP, closure, and you take the orthogonal complement in that space of theta P time delta P acting on H2 of dP. So that's precisely the Nodge-Foyash model space for a completely non-unitary contraction, where this operator here, P tilde, is just the same as in the Nodge-Foyash theory. And S tilde it's the direct sum of this operator that we've already seen, T G star plus Z G, so that will act on H2 dP star, plus some operator U on this second component in the model space, where U and multiplication by e to the it is a gamma unitary. And of course there's more detail about that gamma unitary in the proof of the theorem. But I think that's a really elegant extension of the Nagy-Folyás theory. Now, I should make some comments about my original title, my original title was Models of Commuting Pairs of Contraction, functional models for commuting pairs of contractions. And of course I haven't really got that. This is not really a model of, if you've got commuting contractions A and B on some Hilbert space, this doesn't provide a model for A and B. It provides a model for the symmetrization A plus B comma AB of those two contractions. And of course when you pass from a pair A comma B to their symmetrization, you can lose a lot of information. I mean, you might start with two non-zero operators and finish up with just 0, 0. That could happen. So having a functional model of the symmetrization is not quite the same as, well, it's far from being the same as having, as it were, a simultaneous functional model of A and B, of the two commuting contractions you started with. So that's why I started having a slightly bad conscience about the title that I'd given for this lecture. But fortunately, Vasily saved my blushes by proposing a much more accurate title. So that's a good thing. There are a whole lot of considerations which I haven't really entered into here to do with uniqueness and whether things are canonical and so on. The Nagy-Folyás model is canonical, and if you have there's a unique Nagy-Folyás model for a contraction, and the same goes here. So if you've got a commuting pair of contractions A and B, you form their symmetrization, and then you apply this machine to get a functional model for the symmetrization. That is canonical. If you try and go some other route, so you could start with A and B and take an andodilation, commuting unitaries that dilate A and B. But that's not canonical. That's two different people could do it on different days and get different commuting unitaries. So that's a sort of a slight drawback from the point of view of looking for a canonical theory. This one is canonical, but on the other hand, as I say, you lose information. You're not really getting a model of the commuting contractions that you started with. When should I aim to finish?
It's up to you.
Oh, right.
So,
Well, I don't know. The audience is going to get up and walk out at some point. Right, anyway, just for the last bit, I want to, I more or less finished the operator theory part of it, but I wanted to give you a little bit more motivation why we worked on this set gamma in the first place and got interested in this sort of operator theory. So first of all, here's some references. So you see there are these. It's this thing. Yeah, I see. Yeah, right. Yeah. Oh well, these are references that contain everything that I've been talking about today, and the last 2 days as well. And I think these slides will be. So I had slides of all the lectures, but I decided in the end not to use them. But I believe they will be on the laboratory's website. It may already be, I don't know. But I want to tell you a bit more about the symmetrized bidisc. So far I've been looking at the closed symmetrized bidisc, gamma, but for some purposes it's more convenient to work with the open, with its interior. So it's the open symmetrized bidisc, defined in the obvious way. And this has turned out to have a theory of interest to several different classes of people. So one thing you could be interested in is its contrast, its commonalities, but also its differences from classical complex function theory in the unit disk. The second one, of course, that's what I've been talking about. The third one was actually the one that's made possibly the biggest impression so far. Specialists in several complex variables that study invariant distances, Carathéodory distance, the Kobayashi distance on a domain in Cn, it's turned out to be of great interest to them because it has provided some counterexamples to long-standing conjectures and things like that. But where we originally started, Agler and I, was this one, problem in robust control theory. So here's an example of an interpolation problem that is of interest to control engineers. The 2x2 spectral Never-Ninopic problem. So you're given some distinct points in the disk and some targets which are 2x2 matrices, W1 up to Wn. And it's convenient to assume that none of them is a scalar multiple of the identity. And you want to do a sort of Never-Ninopic interpolation there. So you want to construct an analytic function in the disk whose values are 2x2 matrices, which meets these interpolation conditions. It takes the jth interpolation node into the jth 2x2 matrix. But now, whereas in the Never-Ninopic problem, you would have the norm of f of lambda is less than or equal to 1 for each lambda. You replace that by asking that the spectral radius of f of lambda be less than or equal to 1 for all lambda. That makes it much harder. In the case of the norm, if you replace R by the norm, then the classical theory, the Pick theorem, goes through with rather minor modifications, and you get a very elegant and very well-known criterion for the existence of a function f that does this. But in the case when you replace it, when instead of the norm you have the spectral radius, this problem is unsolved. Nobody knows how to do it. And we made an attempt to solve this problem, and that's what led us to start looking at the symmetrized bidisc. And so the motivation, I think, is fairly simple. So you've got, so suppose, actually, let me draw the set of spectral so this is omega, and this is equal to the set of 2x2 matrices A, such that R of A is less than or equal to 1. So that is some hideous space in a domain in C4, or a closed set in C4. It's unbounded and non-convex and altogether a very difficult domain on which to do function theory. And we're trying. We've got these points lambda j here and these target points w j up here, and we're trying to construct a function f into that domain. And of course, as I say, it's very awkward trying to construct it. How do you make a function f map into that domain? I mean, there are, of course, ways, but how can you get a general way of constructing it? And so we thought, we noted that if you take the map trace determinant on 2x2 matrices, then that will map this set omega precisely onto the symmetrized bidisc. So a 2 by 2 matrix belongs to this set omega if and only if its trace and its determinant belongs to gamma. And so what you could try and do is to construct a function.
Excuse me, is this the mapping 1-to-1?
No.
No?
This one?
Yes, yes.
Oh, certainly not. No, because I mean,
But there is a bit. Yes.
no, because after all, they're invariant under similarity. That's a trace and determinant. So it maps an entire similarity orbit onto a single point.
Is this atomic is connected?
Yes. Yes. Well.
Every operator can be connected with a zero.
Yes. That's right. So you've got this WJ here, and so it will map to a point down here. Under this map, it will map to a point Sj, comma Pj. And so you have the analogous problem for gamma rather than omega. So you've got some target points down here, and you want to construct an analytic map from the disk into gamma that maps these points to these points. And then, if you can do that, then actually you can always lift it up to a solution of your original problem. So that seems like some progress, because this gamma is a much nicer set to deal with than this huge set omega up here. And so we thought we would try and solve this kind of Neverland-Pick problem for gamma. And the hope, of course, was that we would be able to come up with something like Pick's theorem, something like there exists a solution if and only if the following n by n matrix is positive. And that would be the best that could happen. But of course, that's very optimistic. And probably there is no such criterion, I guess. So all we have managed to achieve in the 20 odd years since we started trying to solve this problem is that we can solve it for 2 points. So now if n is 2 there, then actually
For n with kernels, also there is solution. This paper in 2006.
well, but that's not very constructive. I mean, you have, yeah, if you accept some fairly non-constructive steps, then there are ways that you can do it. But if you want a very explicit solution, we can only really do it for two points. So here's an idea. You're trying to solve this interpolation problem. You could do the following. You could consider any map from G into the unit disk. And then you could look at the points G of Sj, Pj. And now, if you had a solution F here, then G composed with F would be a solution of a classical Neverland-Pick problem. And so, a necessary condition for the solvability of a gamma Neverland-Pick problem is that all these problems should have solutions. In other words, you let G be anything, any holomorphic map from G into the disk. And for every such G, the corresponding Neverland-Pick problem will have to be solvable. And so we call that weakly solvable. So if H satisfies those conditions, then we get a solvable classical Neverland-Pick problem. And so it will follow that the the pick matrix corresponding to each of these is positive. Now, and in fact, it turns out that you don't need to look at all possible g's. It's enough just to look at those special ones, phi sub omega, which I introduced, where omega ranges through the unit circle. And that's equivalent. So weakly solvable so this Gama-Neven-Lennepick problem is weakly solvable if and only if this one parameter family of n by n matrices are all positive. But of course that's weakly solvable, and what we really want is solvable. And fortunately, if the number of points is 2, then solvability and weak solvability coincide. And consequently, combining that with the previous theorem, you get that this Gama-Neven-Lennepick problem is solvable if and only if this pick matrix is positive for every omega in the unit circle. So that is, I think, a pretty concrete criterion. So then you say, right, well, let's do it for 3 points rather than 2. Unfortunately, it doesn't work, because we eventually managed to construct an example in which you have 3 points in which the problem is weakly solvable. So for every G like that, you combine the two, compose G circle F. That is a solvable problem, and yet there is in fact no such F. So that's a pity. That's all I can say. So anyway, we still can't do that. So if anyone is inspired to find a solution of this, I mean, it looks such an innocuous problem, doesn't it? Really, or going back. The 2x2 spectral Neven-Lennepick problem, you say, surely it can't be that hard. And maybe there is some clever idea that will do it, but we couldn't find it. So this is another way of expressing that result. If you take this set omega of 2x2 matrices of spectral radius less than 1, you take two points, 2 matrices in that set, and lambda 1 and lambda 2 in the disk, then there's an analytic function from the disk into omega, meeting those 2 interpolation conditions, f of lambda j equals wj, if and only if this inequality holds. So on the right you have the pseudo-hyperbolic distance from lambda 1 to lambda 2, as in the classical Schwarz-Pick lemma. On the left, instead of having another pseudo-hyperbolic distance, you have this rather complicated looking expression. So it's the supremum on the unit circle of a fractional quadratic. So, I'm going the wrong way. This relates, as I said, to the Carathéodory distance and the Kobayashi distance. So if d is the hyperbolic distance, the pseudo-hyperbolic distance, the hyperbolic distance on the disk, then you define for any bounded domain omega the Carathéodory distance like that. You take all possible analytic maps from omega into the disk. You look, so I guess that's fairly self-explanatory, but I always like to draw pictures. So here, this is now a general omega, it's not that particular omega. And you've got 2 points in omega, and you've got, so what do? You look at all analytic maps from G to here. So what did I call those points? Z and W. So you get G of Z and G of W down here. And you look at the hyperbolic distance from G of Z to G of W, and then you take the soup over all G's. And that's called the Carathéodory distance. And an analytic function for which the supremum is attained is a Carathéodory extremal function. And there's a dual notion. Oh, well, I'll come on to that in a minute. Yeah, so the solvability criterion that I just described for 2-point gamma, Neven, and Epic problems can be interpreted as being a formula for the Carathéodory distance on G. And there it is. So it's somewhat messy, but it's the truth. So this is just really just a reformulation of what I've already told you. There's a dual notion of the Kobayashi distance. So I can use this picture. So the Kobayashi distance on omega, instead of looking from maps from omega into the unit disk, you look at maps from the unit disk into omega. So we've got these 2 points, Z and omega, and what you do is you fit some kind of analytic disk here. So you look at all maps, say capital F, from the disk into omega, and you look at the lambda and mu in the disk, such that f of lambda equals z and f of mu equals w, and then you take the infimum of the hyperbolic distance. So I think I called that d, didn't I? The hyperbolic distance from lambda to mu over all lambda, mu, and d, and f, which are holomorphic from the disk into omega, such that f maps lambda to z and mu to w. And well, that's in fact not a distance. It doesn't satisfy the triangle inequality. But then you do the obvious thing and make a distance out of it, and you get something called the Kobayashi distance, which is it's a subject of a big thick book by Kobayashi. And there's quite a lot of specialists in several complex variables who work on this kind of thing. The major theorem in the area is Lambert's theorem, which says that if the domain omega is convex, then actually the Kobayashi and the Carathéodory distances coincide. But that's not true in general, for a general domain omega. But it is true for the symmetrized bidisc. And because the symmetrized bidisc is not convex, and it's not convex in a very strong sense, and it's not even isomorphic to a convex domain. So you wouldn't necessarily, there was a conjecture that for any domain that was not isomorphic to a convex domain, then the Kobayashi and the Carathéodory distances would differ. But this symmetrized bidisc provided the first example to show that that's not true. So these are some further references which are related to this hyperbolic geometry. And the last one there is about the connection between all this material that I've been talking about with a problem in control engineering. But anyway, I won't say any more about that. I think I have exhausted your patience, so thank you for being so attentive for so long. And I think I can finish.
Thanks for you.